In standard physics, particle mass is typically treated as an empirical given, a number derived directly from experimental observation. But the ODTBT framework, specifically Addendum 22.9, sets out to derive these particle mass ratios using strictly structural geometry, resolving two major mathematical problems in the process. Instead of relying on continuous parameter fitting, where values can be adjusted until the math aligns with measurements, this framework demands that mass emerge as an inescapable consequence of spatial structure. The first major test surfaced during calculation, when researchers applied the standard mathematical formula used for determining meson masses to the muon. The result was a catastrophic failure, an error rate of 2,087%. An error that large indicates the mathematical rules cannot be uniformly applied across the board. The equations have to adapt to the underlying physical differences between the particles themselves. The structural solution to this calculation discrepancy is known as the dual formula architecture. Elementary particles, like leptons, possess an undivided nature, modeled by a complex full Pauli triplet formula to capture their recursive streams. Composite particles, like mesons, consist of distinct quarks interacting through a simpler geometric mean. The moment this highly specific elementary formula was applied to the muon, that massive 2,000% error collapsed to a precise 0.032%. The mathematical formulas utilized in this framework are strict reflections of whether a particle is elementary or composite in its physical structure. This brings us to the second problem. The entire mass derivation framework hinges on an electron baseline, and it uniquely succeeds when set at exactly recursion depth 3. Why that specific depth? Look at the source text. Multiplying the frequency modulation parameter by the electron phase strain at depth 3 produces 455/48. That's roughly 9.479, incredibly close to 3 pi, deviating by only 0.054 radians. Sitting near the sign function 0 crossing triggers a sign suppression mechanism, plunging the output into a deep minimum past 3 pi. This makes depth 3 uniquely optimal, 47 times lower than depth 1 and 7 times lower than depth 5. This intense suppression is the foundational prerequisite of the framework. It suppresses the denominator in the equations, preventing impossibly large numerators and enabling the math to output physically correct particle masses. To see if this mathematical anchor point actually holds up in practice, researchers tested it against the global corpus of known fundamental particles. This chart plots mass ratio errors across the dataset. With the depth 3 baseline, 9 out of 10 particles achieve sub% accuracy. This precision holds across particle classes, especially the kaon, measuring an error of just 0.005%. Only one single particle, the neutral pion, remains an open case as researchers work to map its exact structural parameters. Deriving this level of simultaneous precision across diverse particles proves that the depth 3 mechanism acts as a universal structural anchor, rather than a selective data-fitting exercise. So what are the broader implications for physics if these specific recursive depths and dual formulas consistently yield accurate mass ratios? Historically, many models have relied on continuous parameter fitting, adjusting the dials until the math eventually matches physical measurements. In contrast, the ODTBT framework derives these precise results purely from integer constants, rational fractions, and rigid structural geometry. These mass ratios arrive not as free parameters waiting to be tuned, but as inescapable mathematical consequences of the underlying architecture. Addendum 22.9 reframes our understanding of particle mass, shifting it from an arbitrary measurement to an explicit structural derivation. It marks a decisive step toward a geometric understanding of the universe's most fundamental building blocks. For the full mathematical derivation, please see the companion video, Icosahedral Scale Invariance, the Dual Architecture of Particle Mass Ratios.